Now we're looking at example 4 from the 1.2 set of notes. We're asked to evaluate this limit graphically and looking at the table. Now, if we go ahead and just look for some common things like what is our vertical asymptote here, or maybe some holes going on, we don't really know. If you look, you can't really factor out this top, so unfortunately, it's not like we can factor in something and cancel, so there really aren't any holes for this particular problem. But when we're looking for our vertical asymptote, we can go ahead and set this bottom not equal to 0. So for VA, again, we have that x minus 2 is not equal to 0. Going ahead and solving for this guy, we see that x is not equal to positive 2. So we should see a vertical asymptote going on at positive 2. Now let's go ahead and determine if there is, in fact, a horizontal asymptote. Well, we see that we end up with that scenario on top where the degree is larger than the bottom. And as a result of that, we actually will have no horizontal asymptote. So no HA. Looking now at the slant asymptote, anytime your degree is one more than the on top than the bottom, and we can also see that we have a linear on the bottom, we can actually go ahead and use synthetic division to determine what is, in fact, that slant asymptote. Well, I'm going to go ahead and take this value, negative 2, take the opposite of that, throw that in our box, and then use our coefficients from our top piece. So we have really 1x squared. There is no x, so we're going to go ahead and insert a 0x in there as a placement for our synthetic division, and then negative 5 as our constant. So for our coefficients, we have 1, 0, negative 5. It's really important not to forget that 0 because, again, it does act as a placement. Leaving ourselves some space, let's go ahead and draw a bar. First guy, we always just drop down. And then with this number in the box, we're going to go ahead and multiply that number underneath the bar. Then we throw it back up here, right under the next number, 0. So 2 times 1 just gives us 2. And then always adding going down. So again, this is pretty much just how you do synthetic division. You know, nothing really new from algebra. Then you really just repeat the exact same process. 2 times 2 gives us 4. And then you just add going down. So this is negative 1. Now, because we had a value that was, or a quadratic on top, brought it down a peg because we divided it by x, we brought all of these down by 1 peg. So before, again, they were quadratic. Now they're going to be linear. So we end up with a slant asymptote of 1x plus 2, remainder negative 1. But when we're talking about rational functions, we really don't care too much about the remainder, so we're going to go ahead and ignore him. So our slant asymptote should come out to be y is equal to 1x plus 2. Now going ahead and graphing that, we have our y-intercept of 2. Our slope is 1. So we should see something like this. I think the computer is running a little slower just because I've got a lot of applications. But we should see you know, some asymptotes that are kind of blocking certain regions of our graph. Let's go ahead and graph this now. So I've already gone ahead and entered into y equals our function. Here it is. Keeping in mind the parentheses, those are absolutely critical. And then went ahead and graphed it. And again, you can kind of see we have that vertical asymptote at 2. We do have that slant asymptote with a y-intercept of 2, slope of 1. That this graph is actually hugging. Going ahead and getting out now. A moment ago, we said that the general shape of the graph, just looking at the graphing calculator, should have done something like this. So I'm just going to go ahead and graph that. Again, doesn't have to be perfect, but as long as the general idea or image is there. So more or less, that is the image that we see. Now let's go ahead and start discussing some of the things that go with the table. Well, we have the limit as x approaches 2. And when we're saying left side, we're we're implying the limit as x approaches 2 from the left side. In other words, when we see that negative sign by that number. This again is an arrow, a little hard to see. So we kind of need to go ahead and look at some things in a table. That's really where the graphing calculator is nice and handy, where we can go ahead and do that. So we are going to go ahead and hit second table, and notice I started things out at 1.995. This was the value, 204. So something pretty high. At 1.996, we were even getting larger. At 1.997, we were even larger. And these are all values that are to the left or smaller than 2 as you approach 2 from the left. Okay. Getting very, very close to 2 at 1.999, we ended up with 1,004. So you guys can kind of see that in just a short amount of time for our x values as you approach 2 from the left, your y values are getting much, much, much larger. Now, just for the record, if you're kind of like, well, how do you actually change these values so we can kind of see this window? All that you're going to do is go ahead and hit second. Notice it says table set. We want to set our table at a certain value, and we're going to start it out at some value close to that limit that we're looking for too. So I just set it as 1.995. If you wanted, you could set it as 1.996. Doesn't really matter. And that triangle TBL simply stands for how much do you want to change for every time in that table. So I just did 0.001 because when we're starting out at 1.995, then the change in that table is going to be, in other words, the next number is going to be 1.996. So that's simply just what this second piece means. You guys could also do, if you wanted to go by twos, so 0.002 if you wanted to see that, you're obviously welcome to do that. And now when we go ahead and compare things to the right of 2, in other words, when you are approaching 2 from the right side, so you're getting closer and closer to 2, we see that at 2.001 we end up with negative 996, and then at 2.002 we're at negative 496. So, and then just kind of like looking at some of these other numbers, as you approach 2 from the right side, we can see that we start getting larger and larger negative numbers. And I would hunch that as you keep going closer and closer to 2, simply because we have this error sign here, you would go down all the way negative to negative infinity as you approach 2 from the right side. So because our numbers are getting larger and larger and larger on the left, that's going to positive infinity. And as you have numbers that are to the right of 2, as you get closer and closer to 2, it's going to go down towards negative infinity. It actually, in fact, does match what our graph is telling us. We said, here's our table. We said that as you approach 2 from the left side, in other words, as you're getting closer and closer to 2 from the left, we are going up towards positive infinity. For our function f of x. Whereas as you approach 2 from the right side, we notice that as you get closer and closer to 2 from the right, we're getting closer and closer to negative infinity. So the limit as x approaches 2 from the right of our function is going towards negative infinity. All right. Now the limit as x approaches 2 from the left of our function is infinity, like you're saying that. That also implies that it does not exist. And likewise, for our limit as x approaches 2 from the right of that function, when it's going to negative infinity, it does not exist. Because you can't ever obtain infinity. Like, you just can't actually have a limit or cap it off at a certain point. So that's why it is DNE. And as a result of that, the final like answer comes out to be, since there is no common value, then the limit as x approaches 2 of this particular function dn is dne. Notice, for the final answer, we're not specifying left or right. We're just saying the limit as x approaches 2, because again, that was the original question at hand. We looked at things from the left side and right side, but the original question is saying, well, what is going on both sides? Since they're not ending up at the same spot, so it's like as you approach 2 from the left, it's going to positive infinity. As you approach 2 from the right, it's going down to negative infinity. Since they're not matching up, we can't even say that one's like our limit's infinity, because again, they're going to 2 different places. And as a result, that's why our only answer is DNE. At least if, for example, they ended up going to the same spot, much like we saw right here, as you did the limit as x approached 4 without saying left or right, we could actually specify that it was going to infinity. It's a little bit more precise, but that's again because they actually ended up going at the same spot. Here we don't even have that. Here we just, all we have is DNE. All right. So again, that is example 4 from the 1.2 set of notes.